in this waiting time, I would like to introduce Juan, the old man. He is a master of the Jesus 2. Master work of Jesus 2 is famous in the world. And that's a FullProf. Yeah, sorry. I'm FullProf, okay. He worked in FullProf how many years? 40 years. Now he also is a guest professor in Shanghai University. Shanghai University every year, part-time every year for a few months. Maybe next year will be more, longer. Also depend on your health, but I think it's no problem. Okay, we can start now.
Well, we are 79% through. It is half a gigabyte. So maybe we will let Juan start and then I'll put out an email when the upload is over.
Okay. Now, let's start. Welcome Juan give us the lecture.
Well, first of all, I want to thank the people that have invited me for coming. It's the third time I'm in China in the latest months. I will continue to come because I have a lot of collaboration now with Shenji Fang in the University of Shanghai, and we will continue to collaborate. Well, let me start my talk about FullProf, the origin of FullProf, and the future. This is the first part of my talks. Today is dedicated to the FullProf suite, an introduction to the FullProf suite. And the second part, I will talk about the different possibilities you have for working with magnetic structure using FullProf. One thing that I would like to know is how many people here have never used FullProf? Just to see how. All the way up. One. Yes. The major part seems to be using FullProf. Well, no problem. Well, I start. No, it's going down. Yes. Well, the story of that. In fact, I developed software not for doing software, because I was interested in physics and the problem materials, and then I need to analyze my data, and I started to work with the Riedel method a long time ago in Barcelona, and I heard about the existence of this Riedel method that was mainly used for Newton diffraction, but not for X-ray diffraction. And in 1981, Ray Young published a paper in which he claimed at the moment that it was possible to do that also with X-rays. And then I asked him to send me the program just to explore. And then this is what I did. Then I learned plenty of things with this original program. It's the program DBW from Ray Young. And I started to use that program. The program was written in an old Fortran 77, but for me was possible to understand. And I developed more the program at the beginning, trying to understand how it was working, correcting bugs, etc., etc. Then I had a version of this DBW program that I introduced in the Berthaud lab. I was invited from the beginning of the 80s to go to Grenoble, and then I was developing my doctoral thesis at that moment. I finished in 84, and before 84, I was working in Grenoble for synthesizing my samples, etc., etc. And then I introduced that program that started to be used by people in the laboratory, in the crystallography laboratory. And in 87, summer 87, I did stay at the ALL for treating data from D1b, many diffraction patterns together, and then try to analyze the data. And I was invited by Jean Panetier, and we developed a system of software that was called at the moment STRAP. It's a system for time-resolved data analysis, in powder diffraction. Then we had several things. For example, Jean Panetier developed programs for data reduction of D20 and D1b, and graphic. At that moment, the graphics were using tectonic machines, very, very bad, or plotters, things like that. Alan Heworth had a rival program which is called Prof1 and Prof2, the powder system, which is direct evolution of the rival program translated to Fortran. And this was, at that moment, the only program that had the possibility to work a little bit with magnetic structure in a very limited way. Also, there were other people collaborating, Antoniadis and Philol, for doing just fits of the diffraction patterns, and myself that were using this Young program. I call the program Young, Paule program also, and NewFit is a program that I wrote myself for analyzing diffraction patterns. And well, I was working with all kinds of things that we produced this strap system. This strap system you see here, that we were able to treat very old. Now the quality of the data and the quality of the graphic is much better than at that moment, but we were able to analyze the dehydration of materials following doing a small structural analysis as a function, sequential refinements, etc., etc. From 88 to 92, I was at ALL. I got a position as a 5-year instrument scientist in D4 for liquids and amorphous materials, but I was working in all the other instruments, not in that. I convert the program because I did many modifications to the Young program, and I introduced, in particular, magnetic structure using propagation vectors, formalism, in order to be able to analyze incommensurate magnetic structure and so on. And then I presented this program in a satellite meeting of the IUCr in Bordeaux. And after that, in a workshop on the use of neutron and X-rays in the study of magnetism. And in this meeting, I presented FullProf, and I published a paper coming from this workshop that appears in Physica B, and this is the most cited paper at the ALL. Now, 31 years ago, it's quite old now. Well, at that moment, this is the FullProf. You see here Maria Teresa Fernandez Diaz. We perform the possibility to treat very complicated data like this one. This is phase transition in the lanthanum 2 nickel 04. And you see, for example, in that, well, it is not very well. I don't see the, well, doesn't matter. You see the, probably if I put, yes, no, let me just verify if I can work with the laser pointer. You see that? Yeah, no, better for that. Yes, for instance, you see here broad peak and very sharp peaks that were modeled using this kind of approach in order to treat microstructural effect during phase transitions and things like that. All these kind of things were implemented in FullProf. And in this paper, in Physica B, there is a picture like this one, in which you see it's an incommensurate magnetic structure with two propagation vectors, in which you have sharp peaks, broad peaks, etc., etc. That were able to be treated already in 93 and before, and it was the only program that was able to do this kind of treatment. Well, in the middle of the 90s, I moved to the LLB. I was working with Thierry Rouanel, and we developed, I was converting the source code to Fortran 90, and Thierry Rouanel worked with me in order to develop a graphic user interface for running FullProf. It was WinPlotar. Then this WinPlotar program allowed the people to handle directly powder diffraction data and work with FullProf simultaneously. And we introduced also several programs like DigVolt, Treor, BonSTR, different programs that were accessible from WinPlotar, and the people were using a relatively friendly interface for working with FullProf and diffraction, powder diffraction. Well, at the end of the 90s and the beginning of this new century, I was converting the source code completely. I changed the source code nearly at the end of the 90s in another source code using modules using modern Fortran. And I was also developing a library which is called CrysFML for putting the procedure that can be used by other programs. And then FullProf was based mostly in CrysFML. Then we developed at that moment also the BASI reps in order to do some kind of symmetry analysis of the phase transitions and produce magnetic models to be tested, etc. And then also Javier González Plata developed this editor for PCR files, and then we were continue to develop these programs in order to have a suite that was relatively complete for analyzing data. Then this is at the beginning of the century, then we were handling from the point of view of the source code, CrysFML and FullProf 2K. We developed together with Laurent Chapon FullProf Studio. Together with Javier González Plata, we improved at that moment GBondSTR and BondSTR, and then a new WinPlotar 2006 with Oscar Baltuano, who is a Peruvian guy working in the reactor they have in Lima. Well, we continue to work a lot on that, and then this is just what I wanted to tell you about the origin of FullProf. What FullProf can be, for what can be used? It's a program for simulation of powder diffraction patterns. You don't need data. You can simulate data. Simulate that data not only in continuous, where you can add a Poissonian noise to the data in order to do calculation, explore, for example, standard deviations, things like that. You can do pattern decomposition like a Lebesgue fit in order to get integrated intensities. You can do structure refinement. You can use powder and single crystal data with multiple phases and or domains in single crystals. You can analyze crystal and magnetic structure, special form factors. For example, you can put objects that are not atoms can be, for example, you can describe in the high temperature phase of the C60 the scattering density as a development in cubic harmonics, for instance. And then you can use these rigid bodies. You can use also symmetry-adapted modes. This is one of the things that we are interested in here in magnetic structure, in commensurate magnetic structure, restraints, microstructural effect, superspace for magnetic structure. These are recent developments. We can use multiple data sets, simultaneous treatment of several powder diffraction patterns, mixing X-ray with neutron, energy dispersive, time of flight neutron diffraction. We can combine the single crystal and powder data, and then we have also crystal and magnetic structure determination capabilities using simulated annealing on integrated intensity or on profile data. And we can do also, as you have seen this morning with the talk of Javier Campo, polarized neutrons, flipping ratio analysis. You can do that also with FullProf. And we can also treat data with single crystal and electron diffraction, but for the moment only kinematic theory, and that is not very interesting for the moment for that. The people that start to work with FullProf has a major difficulty at the beginning. That's always the case because it's not a program that is guiding you on the treatment. You have other programs that you have to click in sequentially in different places, and then you can just do a calculation without editing any file. But in FullProf, we have an input file in which you have all the information you provide to the program in order to do some tasks. And this is called the PCR file. It's a text file containing all instructions for running FullProf. A good text editor is needed for using the most advanced options. We have, of course, eDPCR. We have some facilities in order to create a PCR file. But in all these GUIs, the new developments are not included because it's too long to develop that for the moment. And then it's important that the people want to work with FullProf is progressively learn the content of the PCR file. The PCR file may be produced automatically for combining different patterns and phases using the utilities SIFs to PCR or MSIF to PCR. MSIF to PCR is something that we will use here because you convert imported SIF to a PCR file just with a click. And also, it may be produce a PCR file from the scratch by using eDPCR. Here is a picture of how is organized FullProf and the program of the FullProf suite around it. You see, you have the FullProf suite. No, but it doesn't work. I prefer that. I have to use the two things. The pointer is not. Here you see this is the FullProf suite toolbar that allows you to access all the program and documentation. We will see that. And then we have a series of programs that can be used from the toolbar. In particular, for example, external programs like Vesta. Vesta can be invoked directly from the toolbar. And you have other kind of programs that I will not spend time here because it's not the topic of this workshop. And here we have FullProf, and FullProf is the main program, and then you have an interaction with WinPlotar, interaction with eDPCR, then you exchange information about that. You can, for example, produce files to be analyzed with FullProf Studio. SIFs to PCR, MSIFs to PCR are providing to FullProf the input files. And you have other programs that can be used. For example, in particular, K-search in order to find propagation vector using powder diffraction. That this is useful for the people. This is the toolbar in which you have a file, for example, select working directory. Normally you select a working directory when you start to work with FullProf, in which you have your data, for instance, and you select a working directory, and you can, sorry, this one is, yeah. You can load the PCR file or recognized file here. Then you have a code of the file and the type. Here, for example, is a PCR file. And you can load, for example, a CIF file, a CFL file for other programs that you have in the FullProf suite. For example, when you click here, you edit the file which is loaded with an editor that you can select. Here you have, for example, when you click on FullProf or in Folds or Globson or WinPlotar or this is Calculator or Basireps, you click on that and the program runs automatically looking at the code file and look for the proper files that you have in the loaded in the toolbar. You have help for accessing the documentation. I will do that just to show you how it works. And an important thing for the first time you install the FullProf suite is just go to the setting. Remember, in the toolbar you have a settings menu, and when you click on settings, you obtain this dialog. In this dialog, you have, for example, how to work if you want, for example, run automatically Vesta, run console mode of FullProf instead of the graphic one. You can run automatically WinPlotar or FullProf Studio, etc., or run automatically Fourier. You do a Fourier map as soon as the program finishes, etc. And then you have to select an editor. When you are working in Windows, Notepad is quite convenient. You are working in Linux, you can use, for example, Gedit, or in Macintosh, you can use text editor, but there are different things. You can put that. This is not needed to be put now, but for example, one important thing, external programs, you have to tell to the toolbar where is the executable of Vesta. And for example, if you want to use maximum entropy using dysnomia, then you have to tell the program where is the executable. And then as soon as you do that, and you save the settings, you are configure the toolbar, and you have the possibility to access to all these programs. WinPlotar are doing plenty of things. I will not explain in detail because we can do that on live, but do many things. You see, you can read that. EDPCR is a GUI for editing PCR file. It has only a limited number of options. For example, Shubnikov or magnetic space group and super space group are not currently available within EDPCR. If you try to open a PCR file in which you have this formulation, it will destroy the data if you go to particular places. But if you don't pass by that, it conserves the initial PCR. Another utility which is accessible from the toolbar is tools. You go to the menu tools and you select something which is called CIFs to PCR. Then you can select a series of CIF files and create a single PCR file with different phases. And if you provide a buffer file, in particular here, a buffer file means a list with the different CIF you want to load, then you can put a buffer file, and you can put browse, and you select what you want to create. Something for working with X-rays. And you see here, you can create up to 5 patterns simultaneously with different kind of things. For example, X-ray diffraction, neutron constant wavelength, neutron time of flight, profile intensities, or integrated intensities. Then it creates the appropriate format of all these things. And then you can combine all these things in different patterns. And it creates a maybe very complicated PCR file with hundreds of lines in which you have to data. Of course, but it is possible. And then that creates automatically a PCR file. Then you don't need to start from the beginning to write the things. You can modify and work. And you have other programs that are not very important for us now because we are in a magnetic workshop, Folds, MOL PDF, Globson for doing different kind of things. You can do, for example, pair distribution function for molecular crystals. Well, one thing that is important is to know that the program of the FullProf suite are not black box-like with a single way of doing the things. You have many possibilities to do the same thing. Then it's up to the user to find his or her way of working. The GUIs are mere helps, utilities for handling the input control files. The learning curve for the use of the program may be steeper than for other programs. However, understanding the content of the input file and making manual changes is much faster than using the GUIs, once the user is becoming expert of work. This, at the beginning, is complicated, but you can combine EDPCR with editors, etc., etc. Well, what is the future of the FullProf suite? I don't know what is the time now, because I have no... Oh yeah, 11:05. Yes, I don't see any clock just for knowing. Well, it's, now we are changing plenty of things in our group, working with the source code of FullProf and the CrysFML. We are moving the CrysFML library. Sorry, I have done something wrong here. The CrysFML library is converted to CrysFML, something more recent. In fact, it's called now CrysFML 2008 because it's the minimum standard of Fortran, the Fortran 2008. It's the latest, and then in fact we are using the latest Fortran standard. Then we are converting that because it's, in that case you use a much modern Fortran using classes, etc., etc. And then this CrysFML 2008 is always evolving, and it will be the core of the new FullProf 2025. But it will be a first version the next year, by the end of the year, which has limited capabilities, but using a new, completely different program. Here, well, we will improve the web page. It's not yet done. Then you have, for example, the classic interface. We have some other toolbar in which we can incorporate also a terminal in which you can do you can mix command lines and things like that. Etc. You can change that easily, the size, and here you will get graphics, etc., etc. Then this is evolving all time. I think I will show you some a presentation that did Nabil, who is working with me. He gave me some videos for showing you what is happening. Let me just go present something which is. Plenty of things that I have here. This is a talk that gave Nebila Yapekacho, which is my colleague working with me, in which he presented PyCrysFML, a Python wrapper for the Fortran crystallographic library CrysFML. This is what we are working, not now, a long time ago we started, but is something that allows you to work, and that the people that are interested in coding, they can use a Python interface for working with all the procedures that you have in the library. Well, let me just go rapidly because it's not, well, this is, yes. This is the way which we're working. Well, the CrysFML library has mathematics, fast Fourier transform, spherical harmonic, local and global optimization, algorithms, least and non-least square routines for optimization. You have many modules for doing that. You have a manipulation of strings of all kind of data. You have tabulated data also for example, standard symmetry information, Hermann-Morgan and Hall symbols, scattering factor, bond valence parameters. You have many things like that. You have a module of crystal metrics. You have also crystallographic and magnetic symmetry. You have a module related to reflections that can generate reflections in superspace, plenty of things with all kind of constraints and things that you can do. Atom and molecules in crystal, you can, for molecular crystals, the structure factors, all kind of structure factor calculation, powder diffraction, modules, special modules, single crystal diffraction, bond valence, simulating annealing, etc., etc. And you have the documentation also that is accessible in a, if you want to explore the interior of the library without going directly to the source code. Yeah, for instance, this is relatively old. This is, you see that you can write a very simple program. This is the program. Oh, sorry, I have forgotten to put these laser pointer. Yes. This is a program that starts here and ends here. And this program gives you all this kind of information that you have seen, for instance, when you open an output file of FullProf, is because they are using exactly the same thing. You set space group, write space group. With two calls, you have all the information that you have in the International Table of Crystallography generated in an algorithmic way. For instance, calculation of structure factors, you can just with few lines, you can read, for example, zip files, and then you calculate the structure factors, etc., quite easily, just using the program. Well, now what we are changing is the GUIs. The GUIs, up to now, we are using Winteractor, which is a commercial library, and then we will move away of this library and use Python side for doing the GUIs. This is, for example, a calculator, magnetic symmetry calculator. Here, you can use that for explore magnetic space groups, commensurate magnetic space group, but now we will have, so, well, this is not what you expect. We are using, for doing this Python thing, something that has been developed by a physicist in Vienna, I think is Elias Rabel, that wrote something that allows you to work very easily with Python and Fortran. It's called 4Py. And then we have well, this is what we are doing now. On CrystallFML, you have a module subroutines, function, classes, derived types, and how they translate to Python. And we are writing all this, and I suppose that by the middle of the next year, that will be accessible to everybody. Then we are documenting at the same time as developing this wrapper. You see, for example, this is a superspace group type, and then you have all the components, etc., and explain and then you can access to all these kind of things. You see, well, this is different things that presented. Yes, for example, you have here a Python, typical Python notebook for working, and then you can just import, for example, from PyCrystFML, import PyCFML general space group and PyCFML metrics. You see that you can handle this kind of things relatively easy. Let me just go to see if it works. Access to symmetry group. I don't know if this is, let me just, No, now it doesn't work. That. Let me just, visualization. Well, this is a program which is in 3D that allows you to count. You can go away from. No, sorry. I cannot launch a video. It's strange. Yes. No, but
so if we escape.
Escape. Yes. No, well, no. It's okay. No. Why is not? Because normally you should appear here.
Should we try?
Yes, it's better. Yes, that is such a case. Yeah. Well, this is a part of the. This is for single crystals in a multi-detector system. You see the reflection appearing, etc. You can handle plenty of things, and this is the kind of okay. Yes. This I can. You can. Sorry. I have to go. It's a little bit complicated for me. This. Let me just. Why is not working? Now, that is not working anymore, or is this? I don't know. Well, it doesn't work. It doesn't work anymore, or what? Huh?
Where's space? Okay.
Is it working?
I think so.
Yeah, let me just.
That's right.
Yes. Well, well, yeah. Yeah, it's just for showing you that, for instance, when we have already, you see, for example, you load this is something for automatic. You have found the indexing, and you will see when it's running, you will see the appearance of, or you can see, for example, that when you move in the detector, you see the HKL in reciprocal space, and when you are changing the position, you see the appearance of the projected reflections, etc. You see the experimental and the places in which you have the predicted position of reflections. Then this is something that now the people from PSI, the people from Munich and ANSTO, they will start to work with this kind of interface that we have developed everything in the yes, let me just go. Yes, for instance, this is when you have a integration, you see immediately the ellipsoidal projection in which you will do the integration of reflections, and the part that you see in white is just the mask that we put around the reflection in order to eliminate, for example, if you have some spurious reflection, etc., can be removed in order to integrate best the things. You see, for example, you can work also with with twins that, for instance, you can select yourself by hand few peaks for twinning, then you will get the orientation matrix of each particular twin, and then you can find the orientation matrix for each domain, and you can do all these kind of things relatively quite easily, quite user-friendly. You have all these. Well, this is the kind of interface that we will put also for the FullProf suite, because we have a common framework for doing all these works. And for instance, if you put now the lattices, you will see, yes, we put that, select a color for the lattice, and the other side, you see here the orientation, the relative orientation, the two lattices, etc., etc. Let us continue. Well, this is also, for example, it's just a look in the detector. This is the detector in 3 dimensions. And this is a particular case which is complicated because it's the terbium manganese O3 at very low temperature. You have a very broad peaks and sharp peaks in a single crystal because you have a correlation length shorter for some magnetic propagation vectors that you see here. That, for instance, this is what I have done. I came back. Yes, let me just here. You will see this is the complete data collection that we did, and you see that they are not streaks, it's really reflections, but they are very close ones to the others, and you will see what is happening here. You have a broad peaks, which are not in the position of the lattice. There are propagation vectors. There are several propagation vectors here. And you see that, for instance, what we do for integrating this kind of things is to take a sort of tube along a reciprocal lattice direction, and then we project something which seems like a powder pattern, but it's just the intensity. And here you have the reciprocal lattice units K, and you see how is the peaks. You see clearly something which is interesting. Is that you have a integer numbers here. You have a sharp peaks, and the integer numbers correspond to the main nuclear reflections, but the other ones are peaks which are more or less sharper, depending on the different contributions. And then you can do refinement automatically of this thing in order to integrate reflection in a sequential way using a program that can be visualized also with WinPlotar. Plans for the new FullProf. When we want to rewrite it from the scratch, built on CrisFML 2008. And the main input file, the PCR file, will be replaced by a keyword value file, which is called the CFL file. CFL is the extension we use for the programs based in CrisFML. We will use a new GUI built with PySide, and the user will be able to perform simultaneously refinement of several phases with different kind of pattern, X-ray, neutron, pattern, single crystal, constant wavelength, time of flight, etc. And also we have also computer algebra included in the thing. We have something, this is interesting just to show you that you can, this is just a test for doing the computer algebra. You have developed a module in which you can write whatever function that can be incorporated into the program, something similar to what is done with Topaz, but you can do that also here. But in for instance, you can, this is just for calculating a pseudo-void function. You write here, this is that you write yourself by hand, and you write the formula that you want to calculate a function, and you can add several functions, you can do plenty of things, and you can use slider for the different parameters that you have, and you can modify to see how it behaves. And then you can put very complicated things, because you can, in the place where you have written this formula, you can redefine in which you have a much more complicated formula. And then you can play with these things in order to see, to explore new big shapes, for instance, etc., etc. Well, then this is not, well, this is Globson, is another thing. Well, it's not important now. Well, I wanted to present you these different things that we have in FullProf, and let me now give you a small, well, I have a, well, you see here, you can open different instances of the same toolbar in order to work in different directories. I'm working the major part of the time in several things at the same time, and then I have to open several toolbars. Well, this is what for instance, yeah, you know here that you have select working directory. This is the important thing in order to work in a particular place. Here we will work, for example, here is one example that Teresa will present later. It's basic reps here, is something in which we have selected the directory, and we have load a PCR file already implemented here. But you can load also, for instance, information files, you CIF or MCIF, etc., etc. You can run different kind of, you can load different files in the toolbar. Here, if we do that, we can edit the file just clicking here. And then you see here on the left, we have the EDPCR file. This is the PCR file that we have loaded. Here it seems complicated, but just to tell you something simple is all the PCR file have you have an exclamation mark telling that it's a comment for the program, and you have a flags or value or different variables, and below you have the value. This is a compact way of writing different things. You see, for instance, in this particular case, we have a single pattern. This is you have a number of faces. We have 2 faces. You have a different kind of things with different numbers that you can write here. And this part is, for example, in the case of constant wavelength, we have here the wavelengths, etc. You have also relaxation factor for the least square refinement. For instance, I put here a short number because we are using angles, not in that particular case, but in other cases we are using angles that move, for example, the structure, rigid bodies, etc. Or, for example, using one of the ways of working with magnetic structure that we'll explain later. You move, for example, a complete reference system with angles, and this is a little bit stable. You are too far from the good position, and you have to control that. You have also the excluded region, some part related to the instrument, the 0, etc. The background coefficients, for instance, this is a Chebyshev polynomial of 24 coefficients. And here you have the phases. Here is lithium, iron, arsenic, 2, oxygen 7, D1B, 2 Kelvin. And here this is just a keyword for telling that in the second phase, there is the magnetic structure related to this compound. This compound, you have here the position of the atoms. You have a different thing here. We have the instrumental resolution function file, which is read here in another directory, and the data are also in another directory. And you see all the things. And here you have the part concerning with the magnetic structure, in which we are using basis vectors of irreducible representations in a simple way. This is a very simple structure, but if, for instance, if we run the program, you just click on FullProf, and that is finished already. You have the refinement, you have a magnetic factors. You can, for example, open, I don't know if, yes, if I open FullProf Studio, it's able to refine to to plot incommensurate magnetic structures. And see, when you put the keyword envelope, you see what is the plane in which are rotating the magnetic moments in that particular case. And here is an example that Teresa will present in which you have the possibility to treat that with Basi reps, with superspace groups, and also with other kind of methods that we have that I will explain in the second part of my talk here. Well, one important thing also that you have here is the help. Help, you have manuals, help files, PDF files. For instance, if you want to have a look on flipping ratios, what's explained by Javier before, you click here and you open automatically the refinement in FullProf using flipping ratios with all the implementations, detail, etc., etc. And an example, and you see part of the PCR file for working with spin densities, etc. You can, whatever you put here is, you can PDF file, you have many, for example, you want to see FullProf time of flight, you will see the formula. You can use, for example, Globson, how to use Globson, this program. Then you see program Globson, and you see a very example, this is a simple file using CFML library, and etc. You can do all these kind of things with HAL. And another more important, the most important thing is that the manual of FullProf is very old and is not updated. It's like that because, but you have news, and you have, when you put FullProf here, news, you open a file which is called fp2k.inf, that is in the main directory of FullProf, and here you see 22 November, small changes in SIFs to PCR. And this is what I had to do because, well, that's different things, and then we have all the modifications are here. And here you can read that time to time just to see what is happening and just to get some examples, etc., etc. This is the place in which each change we do in FullProf is documented. I don't know how long I've been talking. Yeah, but 10 more minutes I have it, yes, before starting, because I start another talk. Yeah, okay. Well, I will continue a little bit, and then we will wait a moment just to see. Well, you have things like this calculator here, for example, magnetic symmetry. This is what you see before. If you want to see a list of magnetic groups, you, for example, you can select what kind of system you can, for example, what kind of, for example, suppose that we want to explore tetragonal system and magnetic space group of type 1, colorless, type 2, paramagnetic, type 3, and type 4. For instance, type 4, you click here. Sorry, I did that, and then you see here the list of magnetic space group of the tetragonal system of type 4. You see the new notation also, unified notation, because we have the BNS, the Opechowski-Guzione, and uni. For instance, if we copy that, or the uni, whatever thing like that, you see control copy, and you come here, and you put magnetic group, control V, you say go, and then you see there's an anti-centering vector like that. You have symbol operators. You see automatically the symbol operators and the element of symmetry with the one which are prime or not, etc., etc. You see that very easily. You can put, for example, suppose that we want to put here an atom in a position 0.1, 0.2, and 0. It's a special position, probably, I don't know, and then you put a moment, 1, 2, 3, and you put that orbit of an atom. You click on that, and you see the position of the atom in the unit cell and how the magnetic moments are changing. All these kind of things are interesting for the people that want to understand really what they are doing. And this is important. You can get, for example, full info, Wyckoff position, etc., etc. And then you see here all the Wyckoff position of this magnetic space group with the position and how the magnetic moment are changing. You see, well, you have facilities like that and many other things that for magnetic things, this is what is important. You can change the setting also, just putting here a formula with a, then you can create another kind of things here. Well, the other things are not important for here. Other thing interesting for magnetic structures, I think here is not. Well, EDPCR, for instance, this is using irreducible representation. That is okay for EDPCR. EDPCR, you can open that, and then the people starting to work with FullProf use a lot this EDPCR. I never use it, but well. For example, you have general here, refinement calculation of powder diffraction pattern. You have a different kind of thing. For example, you want to put simulating annealing, you can create files for simulating annealing, or take a PCR file, save with another name, and start to do changes. Then, for instance, you have a part which is called patterns. Pattern, you see that you can add, you can do data file, pick shape. You see here what we have. Oh, this is the data file. We have data from D1B. You can go, this is a Neutron constant wavelength, pattern calculation. Well, you have a different kind of things here, etc. Cancel. You have the part of phases. In phases, you see, for example, contribution to pattern. This phase contributes to this pattern. And here you can see the symmetry. Here is very simple, no problem. Yeah, the symmetry, this is the phase number 1. But here we have 2 phases. We go to the next phase, which is the magnetic phase, and we go, for example, to symmetry. And you see here, basis function of the irreducible representation of the propagation vector group. And here we have the group we are using, and you see irreducible representation. You see here, plenty of things that we will explain later. You can do that. You can go to refinement. In refinement, you see the background. This is Chebyshev polynomials. You can see this is the atoms. You can refine, fix, etc., cancel. You can, for example, phase 2 atoms. You see here, now it is a magnetic atom, and here you have the coefficients of the irreducible representation of the basis functions to be refined, etc. Here they are refined, yes, etc., You can, for instance, you say, one thing that you have to do when you work with EDPCR, you say, okay, yes, you accept what you have done here, and immediately it's interesting to say save, because there are some bugs somewhere, and then it's better to have a save. And then if you want to see the PCR file, you see input control file here, and you see here the PCR file. If you modify something here by hand, for instance, let me just put something like that. I have changed nothing. If I save and I close, you see the PCR file was modified by external reload the PCR file. Yes, I reload. Then you can play with the 2 things, just editing directly the PCR file or going through the GUI and do different things. You can, for example, output. You can, for instance, change the format of the PCR file. You can select many things in order to work. Well, in my case, it's not important. This is EDPCR. Other things, K-search, we will see that in the tutorials. K-search is looking for, let me just verify if I have already that. Select working directory. I say search solution, I have that in that tutorial. And then here, I think, I don't know, I have it already. No, it's not a problem. Well, I will not use that because I will lose some time on that. Well, let me now stop 5 minutes and then I will restart the second talk. If you have questions during these 5 minutes, okay for me. Well, now I will give you a list of things, not really, we will not work directly with for FullProf now because after me, Dimitri Kalyavin will explain how to work with FullProf in some cases. I don't know exactly, you will be working with magnetic groups or things like that. And then Françoise Damé and also Maria Teresa Fernandez-Diaz will do some tutorials. And of course, you can do these kind of things also. I don't know if you have already, let me just downloaded something that is accessible to all of you. Normally, you will have, this is exercises, and you will have something like a list of exercises with different, for example, if we go here, you will see that you have tutorial on Olmium, this one. And you see this tutorial, you have guides you how to work with that. Then you will download all these kind of things and you will be able to work yourself at home, etc., in order to learn how to work with FullProf. And you have also documents in which the representation analysis, magnetic space group, etc., all these kind of things are explained in a PDF document that are distributed in this list of things. Well, let me now continue. Well, one thing, the major method for working with magnetic structure is doing powder diffraction at the beginning. Of course, when you have a single crystals, you can go to see details, solve ambiguities, etc. But main method for working with magnetic structure is neutron powder diffraction. This is an important thing. And how to work in order to determine a magnetic structure using neutron powder diffraction. You have there, we have a series of steps which are written in red here. Collect a neutron powder diffraction pattern for the sample in the paramagnetic state. It's very important to know the structure, of course. Then you can refine the crystal structure using the collected data and get all the relevant structural parameters using FullProf or whatever program, it doesn't matter. You have to collect a neutron powder diffraction pattern below the ordering temperature. And then normally you will get new reflections and see that something has happened. You have a phase transition. You have a phase transition and then you can try to see how to explain the new, for example, if you have new peaks, then you have to index those peaks. That is the task of the program which is called K-search. K-search means the search for the propagation vectors of the structure. Then this is the third step. You have to determine the propagation vector of the magnetic structure using the program K-search. Over trial and error, if you don't want to use that, you can try just, I suppose that the unit cell is double in that direction, the other, you can try that quite easily, also by hand. But in many cases, mostly when you have an incommensurate magnetic structure, is compulsory to use a program for looking for the propagation vector in powder diffraction. Single crystal is much more easy because you see directly in reciprocal space where the peaks are and you determine the propagation vector easily, but the difficulty is to have single crystal of the new materials. The step 4 is once the propagation vector is determined, then how to start to do or to construct models. The simple and the most extended way of working with that thing was BASIREPS before the existence of all the things that we have done from it was in 2011 in Madrid, in the formation of the Commission of the International Union of Crystallography, in which we try to implement and to disseminate everything related with magnetic space group and magnetic superspace groups. But, for example, you don't know that, you can use BASIREPS, which is quite easy to use. The problem is what to do with the output. That is a difficulty for many people. Once the propagation vector is determined, you can use BASIREPS in order to get the basic vector of the irreducible representation of the propagation vector group. That is also a problem. I don't know if you know what is that. The propagation vector group, the little group, you probably don't know, which are formed by the symmetry elements of the space group, or the operator, that leave invariant the propagation vector. Leave invariant means that they transform it to itself or to another which is equivalent. Equivalent in the sense that the difference between two propagation vectors is a reciprocal lattice vector. That's the only thing. But well, this is the matter of the talk I will give tomorrow about irreducible representation and how to use representation for magnetic structures. Then when you have when you are using BASIREPS, you have two possibilities: commensurate structure, and then you can determine, when you have a simple propagation vector, sometimes you can determine the magnetic space group directly, following some particular rules. The most simple way for people that start to work is to go to the Bilbao Crystallographic server and use one of the programs that you have there, it's difficult to pronounce, MaxMac-N, or K-Sub group MAG, which is that provides you with the list of possible magnetic space group, and you can transform that to a magnetic CIF file, MCIF file, and then transform using one of the utilities of the FullProf switch, which is MCIF to PCR, directly to that. This is the most simple way of working, of course. You can also use isodistort when you have a commensurate structure for do the same, with the advantage that in such a case you combine the representations together with magnetic space groups, because you can understand quite easily at that moment when you are the phase transition, you can think on the physics of the problem, and you can determine which are the important representations that are involved in the transition, etc., etc. You can get, you refine amplitudes instead of, for example, atom position or just the magnetic moment of the atom. You can have things like that. And with the advantage also that the constraints are automatically taken into account. The symmetry constraints are automatic. When you have the list of basis vectors and amplitudes, you just have to refine the amplitudes, that's all. In the case of an incommensurate structure, you can directly use the output of BASIREPS for constructing a model of incommensurate magnetic structure using the basis vector or complex Fourier coefficients. Other options are those that allow working with particular form of magnetic structure. We have also possibilities to work. I will explain that a little bit later. Now, for incommensurate structure, it's also quite easy to use isodistort for working with that. Isodistort at present is not producing a PCR file but it produces a SIF, magnetic SIF, and then you can convert that to PCR. In the future, we will have do something similar to what we had done with commensurate structure, is to use the superspace group together with the amplitudes of the modes also, which will be more interesting. But well, for the moment, it's not like that. Then it's quite simple, but one important thing that you have to keep in mind always is isodistort. It converts everything by default to the standard setting that it has. And this is normally not the setting that you are using. It was explained also by Manu Perez Mato yesterday. And then this is very important, that if you want to conserve the setting, you have to do something that I will explain a little bit later. Sorry, I forgot. Well, then for solving, you have this BASIREPS or isodistort or the Bilbao Crystallographic series produce a list of possible things. Then you can try to solve the structure just by trial and error, just put in some arbitrary values to see what happened, and just look at the diffraction pattern, or things like that. Yeah. Well, there are some explanation here because you will have this document. I will not repeat here because I'm a little bit late now. We can, for instance, well, at the end we can use, for example, when we are not able to solve the structure by trial and error, is because, so for example, we have too many magnetic atoms in the primitive unit cell, and we have relatively low symmetry, and you cannot start to refine or to test by hand. And that in such a case, you can use simulating annealing, adding at the beginning an additional phase in the powder diffraction pattern. You put the nuclear phase fixed, everything, and then you add an additional phase in the biofit mode, in which that will provide you a list of integrated intensities and also some information in order to prepare the simulating annealing work. When you do simulating annealing work, this is done the work for you. At the end, you have something, it never diverges, always produce something that will be interesting or not. It depends on your data, etc. And at the end, you have to refine. When you have something which is reasonable for starting, then you can use the Rietveld method and refine the magnetic structure. Well, which are the different ways for doing that? For example, we have up to 8 different ways of working with magnetic structures in FullProf. The standard Fourier coefficients refinement with this vector Sk described with component along the directions of the unit cell. Then you have a keyword which is called JBT, that may be 1 or 10. Then, depending on, when you use 10, you mix, you don't have a separate phase, you have a single phase, the nuclear and magnetic in the same description. You can, if you change the sign, JBT equal to -1 or -10, you use spherical coordinates for the magnetic moments instead of the components. The second way, it was very old, it's obsolete now, because we were using time reversal operators, but without knowing the magnetic space group, or just you construct them by hand, the magnetic space group. This is obsolete now. The third method is use Shubnikov for magnetic space groups using the BNS formulation is JBT equal to 10 plus IC equal to. These two numbers tells you that the rest of the PCR file described in this phase is for working with magnetic space groups. Then whatever space group in any setting, the PCR file may be generated on an MC file. Then you have other methods that are people that are not familiar with the structure, the symmetry, crystallography, but they use also. Because, for example, you can use real space description of uniaxial conical structure. This is the first incommensurate magnetic structure. It was done by Hastings a long time ago. Then they produced a way of describing that using conical structure. JBT equal 5 is for describing uniaxial conical structure. Then you have something when you don't need a symmetry, just to put some constraints. You have also real space description of multiaxial helical structure with elliptic envelopes. You have this possibility, and this is JBT equal to -1, -10, and more equal to 1, and L equal to 2. There you have several things like that. And then you have also the sex. This is the refinement of coefficients in this expression of the Fourier coefficient in terms of the basis vector of the irreducible representation. This is the number 6. 7, refinement of the magnetic structure using symmetry modes. This is very interesting. This is using isodistort as an intermediate program in order to get the list of basis vectors. Is JBT equal to -6 and IC equal to 2. And finally, refinement of the magnetic structure using superspace groups is JBT equal to ±7 and EC equal to. This is what you have 8 ways of working with magnetic structures. The standard one is something like that. The Fourier components of the magnetic moment of an atom, J1, that transform to the atom Js when the symmetry operator of Jk is applied, you get that, is transformed with that. You have a matrix and a phase factor. This is something before having the superspace group that replace partially the magnetic superspace group. And you work always in 3 dimensions. When you are able to construct these matrices can be constructed by hand from the output of passive reps, and you will see that probably in the tutorials. Then you have the magnetic structure factor, which is written like that, which is a totally general, working in 3 dimensions, and you have this. Then this is, for instance, what we have here. This is a part of PCR file. It's corresponding to the holmium 2 barium nickel 05, one of the tutorial. And then what is written in red there is JBT equal 1, IRF equal to -1, IC equal to -1. That corresponds to the use of the Fourier coefficient, the standard Fourier coefficients. And you see here the matrices, SIM, you have the symmetry crystallographic, and MSIM is not a magnetic symmetry. It's called MSIM, but it's a transformative. It's a transformation of the Fourier coefficients. And you see that you have a number here which corresponds to a phase in units of 2 pi. And you see that let me just show you. Here you have the real components of the Fourier coefficient, and here below you have the imaginary component. Here there is nothing, because this particular case is number of propagation vector is equal to 1. When you say 1, is that k and minus k are equivalent. And then in such case, you should have real numbers, and then you don't have any imaginary component for the Fourier coefficients. here you see the propagation vector at the end here, what you have, you work with propagation vectors. Sorry, what is that? Yeah. One important thing is that, for instance, when you have here situation like that, one single propagation vector, in many cases you have these matrices correspond to the rotation matrices of the Shubnikov group, of the magnetic space group, described in the unit cell of the parent, like in the OG settings. It is equivalent, but instead of using time reversal, we use the propagation vector. It's the same. Well, this is the symbol of the phase group. When you are testing, you put here a symbol which is just for generating the fundamental reflections. And then in that case, we don't know the symmetry at all. If generation of the parent reflection, in this case, half reciprocal lattice is generated. Here, for example, this is the aspect of the PCR file when we use magnetic space group in the PNS formulation, or in which we use the magnetic unit cell. This is automatically constructed normally when you import a magnetic sieve that can be obtained from the Bilbao Crystallographic server, and here it converts automatically the sieve to this kind of information that you have here. You have a number of independent symmetry operators here, number of, this is centering lattices, centering vector, it's a one centering vector, is 0, 1 half, 1 half. That corresponds in fact to the propagation vector in that case. Here is a number of anti-translation. This is what you have. This is the propagation vector in such case is 0, 1 half, 1 half. But these are the anti-translation, and here you have the symmetry operator. With this information, the program constructs the full group and then refine. When you see, for instance, is JBT equal to 10, is obliged, you have to use that, and you have the magnetic moment here in that part. Here you have, for instance, here is this Procyon atom, I don't know whatever is invented. And you have these vectors. Then normally, the program will apply the constraints automatically. Another way of working is the real space description of multiaxial helical structures using elliptical envelope. Then you have a particular way of defining the Fourier coefficient, and that transform to magnetic moments and angles instead of using the complex things. You see that. Well, I did not explain that in detail, but you see how is the PCR file using these see here, for instance, you see here the data. There are two values here. They are the same. It's a circular envelope for the helical structure, and here you have these numbers 15 and 25 here that correspond to angles of the normal to the helix plane. Well, this is the same, more or less. This is using the multi-axial helical structure, but using JBT equal to -10, and then you have this angle here. And, well, it's not coefficient of basis function. You have well, you will see now how you have this JBT equal to 1, IRF equal to -1. -1 means that you generate only satellites. And IC equal to -2. Here is the aspect of the PCR file, and this is what you get automatically when you use irreducible representation. Here we have two basis vectors corresponding to this. These are corresponding to a particular position of Olmium here in that case, and here you have a C1, C2, C3, and you refine that. C1 makes reference to the first base vector, C2 to the second base vector. symmetry modes. This is very interesting, and you have two examples, I think, in the list of tutorials. Dysprosium iron, tungsten oxygen, and holmium barium copper oxide. And then you have all these data are distributed in the tutorials, and you have the step you have to follow for doing that. It is more or less, I do that quite rapidly. Then you have to select, in general, displacive and magnetic distortion of all atoms. So a magnetic distortion. Then all atoms experience, in principle, displacive mode. And only those that have unpaired electrons have magnetic moment. And you have to select that. An important thing that you have to do in isodistort when you select, you make a change, is to click on change. Otherwise, it's not applied. When you click on change, then you can go directly to look for the propagation vectors in the brilliant zone point and set independent incommensurate modulation to 0 here, because it's not for incommensurate structure. This is only for commensurate structure. Yeah, in this particular case, it's 0, 1 half, 1 half, and then all this kind of thing. When you do say OK, then you enter in another kind of things, and at the end, you have the possibility to download directly the PCR file. It's already written by isodistort. And this is the output of isodistort for FullProf, and you see here that what informs the program that we are using symmetry mode is JBT equal to 6 here. Code of symmetry modes. And here you have for the parameter 66 is the total number of amplitudes we have. Displacive and magnetic. And here this is the aspect of this is the standard structure. You see here magnetic space group symbol. You have the symbol, and you have also transform from parent, and then FullProf uses this information in order to construct the magnetic space group corresponding to this particular setting that we want to use, that normally we have selected in isodistort a way to conserve the setting that we have in the parent structure, in the paramagnetic structure. For doing the same thing with superspace, you use isodistort, and then at the end you have to download a zip file and convert to PCR file using the utility mzip to PCR. Here, for instance, is the case of dysprosium manganese 6, germanium 6, which is relatively complicated. You have that in the tutorial, but for people starting to work with that, it's not a simple case. There is another one which is called the lithium iron arsenic and oxygen is much simpler. But this one is complicated because you have many possibilities of superspace group and you have to test many things. And for instance, we provide a zip file with a paramagnetic structure to isodistort. We select, in that case, we have selected only magnetic, no displacive ones. And then, well, we have, in that case, you have two propagation vectors, because we have a propagation vector 0, 0, 0, because you have a nuclear reflection that increases the intensity, and also satellites. This is because it's a conical structure, in fact. Then you have to provide that. Here, the number of incommensurate modulation is 0. And here, this is the propagation vector of the satellites. You provide the number, the component of the propagation vector, and you have to put here 1. If you put 0, it doesn't work. You have to put that 1. And you can also put different superposed irreducible representation, and then you have to put a change and add another thing. Is more complicated. When you click on OK, you enter in another dialog in which you have the list of different irreducible representations. then you, here in this case, is complicated because you have many possibilities. And then you start to work with each one, and then you can, or for example, you can, once you have this, because you have the possibility, you have two superimposed irreducible representation. In that case, in fact, you have two propagation vector that correspond to GM. The gamma point is the k equals 0, and this is the k equal different 0. And when you do that, at the end, you produce a C file, you export, download the C file, and then using the utility msif2pcr, you get a PCR file. And the PCR file for incommensurate magnetic structure using superspace group has different blocks. And then I will describe rapidly the blocks. You have a block, this is the symmetry block. The symmetry block, you have this is, for example, the number of atoms. JBT equal to 7 is to tell the program that we are using superspace. You have in that particular case, we have a single propagation vector. This is not true because the 0 is assumed always. If we have only one satellite. And here we have not to put -1, like in basic reps, because here, necessary, you have k and minus k. And here you have a particular magnetic superspace group, and here this is the operators that have been downloaded from ISODistort. You have the number of Q coefficients, a lot of things that, of course, for using this kind of thing, you have to learn before, because otherwise you don't know what you are doing. And here this is the aspect, the thing. For example, you have an atom. Here, when you put here -1, this is the number of modulation function that you have. When you put negative, it's because you have a displacement also. But this is not, it's implemented, but it's not calculated presently in FullProf. This is for displacement. Here is mcos, msin. You have 3 components and 3 other components here. This is the cosinus part, and this is the sinus part. 6 components that correspond to the Fourier coefficients, which are complex vectors, which are also 6 components. It's the same. When you have the different, this is the atom blocks in which the part considering. Here you have always Mach M0 moment that correspond to the homogeneous magnetic moment that correspond to the propagation vector equals 0. And then you have finally the propagation vector block, which is this one, in which you provide the value of the propagation vector block. You can put, for example, the sinus theta limits in order to limit the generation of satellites, because in many cases, if you have a long range, you cannot, well, the magnetic structure are negligible, the intensity, and it's a waste of time calculate magnetic contribution at very high Q. Well, when you put, for example, automatically, when you want to apply that, in the program you can introduce the instruction vary mx, my, mz, or mcos, msin, and the program applies from the list of operators, deduce the constraint you have to apply to the modulation vectors. Here, for example, is a test. You see that the refinement is not good at all, then you have to discard this magnetic space group. And then if you start to, well, these are some explanations, you start to continue to work with the different, and you arrive to this one, P622 prime, 00 gamma, H0. Then you see here that you have many possibilities with this hexagonal magnetic group, but at the end you arrive to the solution. This is by trial and error. Well, For different options for describing the magnetic model, yes, in the documentation that I provided in the list of files that you can download, you can read this magnetic structural analysis and refinement with FullProf. Then there is a document in which you have all my talk here and more details, and then you can work with that. And I think I will stop here if you have some questions. I don't know how long we have still before lunch.
Exactly the correct time.
Yes, now yeah, I finished at the correct time.
And 12:20, so it's very good right now.
Well, if you have questions.
Now I have a question.
Wow, yes? I'm here because I don't hear enough. I have a problem with my ears.
In which situation should I put NVK equals 1 or -1?
Yes. If you are using superspace, you just put the number of propagation vector. Of course, you put one propagation vector. That means that, of course, -k exists always. In the case of using the traditional way of working with FullProf, you put -1 when the propagation vector is inside the brilliant zone. It is in the surface, and the difference in the k is equivalent to -k, you put 1. K equivalent to -k means that 2k is a reciprocal lattice point, or lattice.
So if it is equivalent, should I put -1?
For example, suppose that you have if you have a primitive cell and you have a propagation vector 0, 0, 0.23, you have to put -1 and write only 0, 0 pointer. But you have to put -1 in order to inform the program that you have to work also with the -1, because it's not implied that in the traditional way of working. You put -1 when you have a vector inside the Brillouin zone. When you use Fourier coefficients, many other things. When you use superspace, you put 1 or 2. It depends on the dimension of the superspace you are using. You have a superspace with 2-dimensional, but then you have to put 2 in that case. And in the case you are working with the traditional way, then you have a place in the PCR file to tell which propagation vector corresponds to the coefficients you are giving. It's another, more complicated in the other case.
Another question is, you have 2 examples using isodistort. One, you click displacive for the atoms, also for the magnetic. So another
yes,
one is
in some
only
cases,
magnetic.
well, you put magnetic and displacive because you may expect normally when you have a magnetic ordering, you have a magnetoelastic coupling, and then you will modify slightly the crystal structure simultaneously. In many cases, it's not detectable. You cannot find that. And if you are sure that your crystal structure is well described by the paramagnetic state, just changing a little bit just the coordinates, in such case you can put only magnetic modes. You put only the magnetic modes because the magnetoelastic coupling is small. But in cases you have a strong magnetoelastic coupling, it's interesting to refine also the magnetic structure using new representation that appear, not just the gamma representation that correspond to the normal structure that you had in the paramagnetic state. Then sometimes it's interesting to know if you are able to refine, or in many cases you can always do that, because if you go to the difference between the paramagnetic state and the temperature You have, for example, you have a magnetic ordering at 120 Kelvin, and you want to refine the structure at 1 Kelvin. There is a long distance in between the two in temperature. In such a case, you can refine the crystal structure using modes, just putting what you had at 120 or more, fix the crystal structure and refine the displacement amplitudes in order to adapt to this difference in temperature. But you have normally other modes that appears and you can try also to refine, but these modes are much more difficult to detect, and normally the amplitude, the standard deviation you have in the amplitude is bigger than the amplitude, and in such case you can keep the amplitude equal to 0.
Okay, thank you.
One more question.
Hi, Juan. So there's many different versions of FullProf, and sometimes I found. Can you hear me? Yeah. Sometimes different versions of FullProf they don't compatible with each other, right? The PCR file I generated, for example, the PCR file generated for the old version was not suitable for the new version, right? So
I don't know. You have to show me that. But normally I backward compatible. Normally can be converted, but it may be cases in which you have some things that are no more supported. But it's strange. You have to show me what is the case in which you have something which is different.
Do we have a template PCR file for the new version? Or?
The templates. Well.
Yeah. That would be
well, it depends on what you. For example, you are using MSIF to PCR, or what program you told? FullProf or MSIF to PCR?
FullProf, the PCR file to refine in FullProf. So I always confound the data. For example, the lines where you should be the real number, you put it should be the integer number, you put the real, then it will be always complain, and you don't know what happened.
You will show me your particular case just to see exactly, because I don't know.
Okay. Thank you. Yeah, we'll talk.
Well, because of time, if you have any question, you can discuss with
Juan.
And I think this program is very complicated. So I know. So if you want to run program very well, you need to do a lot of the homework.
Yeah,
right?
That's easy, yes.
Okay. Thank you.
Thank you.
Juan.
Just to make sure, download the TOF tutorial and make sure your FullProf runs, because after lunch we are doing tutorials, okay? Thank you. Go to lunch now. We come back at 2.